So we are going to start with this problem. We have a charge, a total charge Q, but this is distributed uniformly over a thin rod. Okay, so there are some keywords that we are using in here, so I'm going to explain what it means. So first, a thin rod means that the rod has a physical thickness in reality, but we ignore it. So as a result, we are assuming that that thickness of the wire is much smaller than the relevant other relevant length scales. So in that case, for example, the length of the wire is one length scale. So the thickness should be much smaller than this. And also, there's another distance in here. The distance of the point from the tip of the rod, that distance A, that also has to be much smaller than the thickness. So the thin means I can neglect the thickness. Mathematically, that's equivalent to taking the thickness to be equal to 0. Okay, so thin rod. So essentially, we have a one-dimensional charge distribution over a length of some object. So we have a rod with length L, so it's distributed uniformly, which means, well, basically the charge density is the same everywhere. So to actually express this mathematically, we have to use some kind of a construct that we call as the charge density. So since this is not a volume charge density, but it's a charge density per unit length, we basically use a lambda symbol for it. So that's basically amount of the charge per unit length. So basically, we just choose some kind of some portion of a length of the wire, just compute the amount of the charge in here and the length of the wire, and so therefore this is Q divided by that length. And uniform means that this charge density does not depend on the position. So let me first write this thing down. So this is called the linear charge density. Okay, linear meaning that it just depends on the one of the dimensions, length dimensions of the object. So later we are going to define the areal charge density and the volume charge density, but this is the linear one. Why do we use the symbol lambda? Because L is like the letter L corresponds to letter lambda. Lambda in Greek alphabet, and that's why we are using this letter in here. Okay, so the linear charge density. So therefore, this uniformly means that linear charge density is constant. Okay, so in this case, since the total charge is Q and the total length is L, the linear charge density is Q divided by L. In any case, in my derivation, I'm going to use lambda quantity, but since the problem is actually did not define a lambda symbol, but expressed the problem in terms of this Q and L variables, at the end, I'm going to replace lambda with Q divided by L. But for now, I'm just going to use this quantity in here. Okay, so what we do is we have a rod, we have a point along this axis in here, along the infinite line where this rod is placed. That distance is A, length of the rod is L, and we would like to find the electric field. Okay, so how do we use the recipe in here? So let me draw the rod in here. So let's just remember the recipe in here. So the recipe basically is saying that the electric field at that point is given as 1 over 4 pi epsilon 0 dq divided by r squared times the r unit vector. Okay, it basically tells us that I have to divide the charges in here into small pieces. For each piece, I need to compute the direction of compute the electric field produced at that point, and then I have to integrate. And I'm going to show you how we can do this. So the first thing is perhaps about the directions. Let's just forget about this. So let's first talk about the division. So divide the charge into small pieces. Okay, so let's start with this. So for this, I need a coordinate. This is usually will be the integration variable. I'm going to do an integration over this variable. So I'm going to choose this as the Cartesian x-coordinate. So as a result, I'm going to choose a reference frame in here. I'm going to place the origin right at the left end of the rod. It's just a choice. And I'm going to choose the x-axis as the direction along which the rod is oriented. So there is this y in here, and there's also a z-axis, but the other two directions are irrelevant. So only the x-axis is important in here. Okay, so that's the first step. So we have to choose a coordinate. The second one is basically I can describe the charge, a piece of charge, a piece of rod in here, by describing the relevant coordinates in here. So for example, if I choose this segment in here, which basically corresponds to some kind of a interval in position, so I can write down the left x-coordinate of the left end of the charge and the x-coordinate of the right end of the charge. So I'm going to write down the left end as x and the right end as x plus dx. So I usually say it like this. So consider all charge in the interval. So x and x plus dx. Think of it as some kind of a mathematical symbol. So it doesn't matter whether this is a closed interval or an open interval. That's not it's not of any concern to physicists, basically. That's an irrelevant thing. So what is dx in here? Dx at this point is some length which is quite small. So dx is basically the length of that interval. So why did I call this as dx? Because at the end, I'm going to take the limit where this dx, this length goes to 0. Well, it will basically appear at the integral, and when I'm taking the integral, implicitly I'm taking the limit where this thing is going to go to 0. But in any case, so we don't explicitly take a limit, but in any case, since this distance has to be small, I'm just using this differential symbol in there. So that's kind of important. Because at some stage we are going to basically neglect this length in here compared to the other lengths. Okay, so let's consider all the charge in here. Next thing is this. So this is the point in here. So next we consider the distance of that charge to the point in question. So let me redraw this picture again. So this is my rod. I'm considering all the charges in here. So I'm exaggerating in here. In reality, dx is extremely small, and I have a point in here. Okay. So with the yellow color, that distance is r. I can easily compute what r is. Let me do that. Because I know this length, this is a. I know that this distance is L minus x. So therefore r is equal, sorry about this. R is equal to a plus L minus x. Okay, this is one of the variables. Basically, I express every quantity in terms of my variable coordinate and in terms of the other constants in here. Okay. So the distance of the charge to the point is a variable. I express it in terms of my coordinate. In that case, it's x. One of the typical questions that I get is whether why don't we have a dx in here? So a lot of people would actually write this thing down like that. So they usually think of the distance to the midpoint of that charge, in which case this is going to be L minus x minus 1/2 of dx. In reality, yes, that's the correct expression, but we are going to take the limit where dx goes to 0 at the end. So as a result, that length, when it is written next to other finite lengths, is always negligible, right? Because we just call this as a differential. So anything that I add to this is basically is negligible. So we should actually, I mean, these kind of expressions never contribute anything to the value of the integral, and so as a result we just drop them, and that is why I just wrote this distance as in this form without any dx appearing. Okay, so that's one of the variables. The second one is, let me use a blue color for that. So there's an electric field in here. Usually the electric field produced by that infinitesimal charge is shown by dE. D in here does not actually imply a difference of some kind of a electric field function. It basically is a reminder that this is extremely small, just like dx is. Okay, even though this dx in here is a differential, this dx is actually is the difference between two coordinates. So it's a differential basically. It's a difference of something, difference of the x coordinate, difference between the left and the right ends of the coordinates of that charge. But this dE in here, it is not a difference. And so as a result, in dE, we say that D is a reminder to us that dE is infinitesimal. Infinitesimal meaning that when dx goes to 0, when we take the limit, this also goes to 0. So it's basically as small as what dx is. Okay. So what else? I think I'm going to draw the picture again. Sorry about that. But let's quickly do this. Again, rod. I have my point in here. We have the charge dq in here. And I'm using this blue color for expressing the dE. Okay, there's also a charge in here, so I also need to find what charge is. So this is the charge in that length segment. So I know that since the length of the segment is dx, I know that this is lambda times dx. Okay, so I know also that the lambda is q over L. So as a result, at the end, I'm going to replace lambda with q over L. But to make things simpler, I'm just going to use lambda in here and insert the value of the lambda only at the very end. Okay. So in any case, so I know that this dE in here, the electric field produced by that charge, is given by usual Coulomb formula times the R unit vector. Okay. At this point, I can replace everything, every expression in here, in terms of the their values in terms of the integration variable. Okay, so dq is lambda times dx. Lambda is a constant. R is a plus L minus x. So as a result, we have this. And then the radial unit vector in here. So this is the radial unit vector. This is always equal to the I unit vector because this is the direction of the x-axis. So as a result, this is I. Okay. So I'm going to rewrite this thing down again. So instead of doing this, I could also write down the x component of the electric field. It's going to be the same expression again, actually, but without the unit vector appearing in here, and without a vector expression appearing on the left-hand side. So the x component of the electric field is basically given by this expression. So instead of integrating this, I'm going to integrate this. So for this problem, it doesn't seem to be important, but for other problems where the direction of the electric field might be changing depending on the piece in here, this is going to be important. And so as a result, we should always try to integrate the Cartesian components of the electric field. Okay, so there's one more step in here. So that's the division part, and then we integrate. Integrating means, well, basically summing over all of these overall contributions, overall possible charge values. So that means I need to change this x value, and I need to change it from some smallest value to some largest value. So that's the next step, basically identifying the integration bounds. And so as a result, we have this expression in here, which has to be integrated. So at this stage, we have to look at this expression and see if there are any variables other than the variable of integration. So here the variable of integration is x, and all the other quantities that appear in the expression are just constants. Okay, so we don't have any other variable. If there are other variables, then you have to try to express them in terms of the x variable. Right, let's continue with this. So this is like, let me take these things out. So I know that this is the minus second power of some linear function of x. I know that this has an integral like that with a minus 1th power. To find the coefficient in front, I just take the derivative of that expression. So that means I get minus 1 multiplied with the coefficient of x in here, which is plus 1. So the coefficient in here is equal to plus 1. So that's the integral. I have to evaluate between this thing between x equals L and x equals 0. So therefore, this is lambda over 4 pi epsilon 0. I'm going to insert L in here, a plus L minus L, and then subtract a plus L minus 0. So as a result, this is lambda over 4 pi epsilon 0. I have 1 over a minus 1 over a plus L. So you can easily see that this is equal to L divided by a times a plus L. So therefore, the x component of the electric field is lambda over 4 pi epsilon 0 L divided by a plus L, a times a plus L. Is this the end? No, because lambda is not given to us, so I have to express in terms of the given quantities. So therefore, the electric field is 1 over 4 pi epsilon 0 Q divided by a plus L. So that's the x component of the electric field at the point in here. Okay, you can basically, once you know the x component, you also know the electric field itself. And so as a result, this is the end of the problem.